Welcome to our discussion on volume and surface area. So previously we've looked at two-dimensional figures and their attributes, i.e. their area and perimeter. Now we're going to take it up a notch and look at three-dimensional figures and get kind of their corresponding things, right? So instead of a perimeter for a two-dimensional, we're going to get surface area for a three-dimensional. Instead of area for a two-dimensional, we're now going to find volumes for three-dimensionals. So a lot of the same techniques will come out, and we'll see that the formulas are very same as well. Okay, the volume of a three-dimensional object is the amount of space occupied or consumed by the solid object, and is measured in cubic units. So that's the big thing to remember, is things are now going to have cubic units. So cubic inches, cubic centimeters, cubic meters, cubic yards, cubic feet, right? Whatever your unit of measure is, there's going to be three of them because we're going to be measuring all three dimensions. Now, any kind of rectangular solid, something that looks like a shoebox, whether it's a perfect cube or not, which is just a special version of a rectangular solid, the volume is always the same, length times width times height. But, as I've said in a previous video, instead of thinking of them as length and width, I thought of them as base and height. Well, now, when we start looking at solids, instead of thinking of length and width and height, think of it as base times height. Only now the base is the entire surface rather than just a line, right? When we were talking about just a rectangle, we had a base and a height of that two-dimensional object. Now the base becomes the area of the base, right? So the volume is area of the base times height. Well, area of the base in this case is length times width. Now you're thinking, oh, you're just confusing the hell out of me. Well, think about it for a second. If you find the area of the base, multiply it by the height, that's the same thing as length times width times height. So it is, in fact, the exact same formula. But the reason why it will serve you better in the future is there are other objects that aren't these nice, simple, easy, rectangular solids, and they have seemingly more complex formulas. But if you always think about finding the volume of what we call a rectangular solid as base times height, then when we give you other shapes, you know that all you have to do is find the area of that base and multiply it by the height and its volume, right? So you don't have to memorize 7 or 8 different formulas. You just know that all of them come down to area of the base times the height, and the only thing that changes is based on the shape of the solid. You have a different shaped base, so you find a different area of that base depending on what the shape is. If the shape is a rectangle, you know it's length times width. If it's a triangle, you know it's 1/2 base times height. If it's a circle, you know it's pi r squared, right? There's all these different shapes now boil down to just simply area of the base times the height. Even a cube, because the area of the base is just s times s, right? S squared times the height, which is also s, and there's your s cubed. Okay, sphere, totally different. Not a rectangular shape, right? For one thing, there aren't any 90-degree angles in this bad boy. So we have a completely different volume formula, and it's 4/3 pi r cubed. You just kind of have to memorize this one. There's no easy way around it. There is, however, a nice relationship between volume and surface area, just like there was between area and circumference of a circle, if you know a little something about calculus and how to take derivatives. But in any case, here's our first rectangular prism. We call rectangular prisms anything that has a base and a top that are parallel, and the sides, the vertical sides, are straight up and down, right? They're 90 degrees with the base. So you can see that the base sits on the floor. We have 90-degree side for the cylinder, and the top of the cylinder is the same shape as the bottom of the cylinder. So this is what we call a rectangular prism. This rectangular solid is a rectangular prism. So the rectangular prism is just kind of a generic term that puts them all into a similar family. You can see that the base here and the top are parallel, and the sides are 90 degrees, right? Same thing. The bottom and the top are parallel to each other, and the sides come 90 degrees off of that. Of course, a circle doesn't work. It doesn't have a top and a bottom. So whenever you have a rectangular prism, the volume of it is always the same thing. Area of the base times the height. So now when we have a cylinder, the area of the base is the area of the circle, which is pi r squared, times the height. So you see what I'm saying about instead of having, 4 and 5 and 6 different formulas for these things, if we just think of it as area of the base times the height, we can see how it's really the same formula each time. We just have to find slightly different, formulas for the areas. Okay, now how about a cone? Well, they're all in the family of pyramids. This is a circular pyramid. This is a square pyramid. You can have a rectangular pyramid. You can have a hexagonal pyramid. Basically, you can have any pyramid shape. Just depends on what the base shape is. Well, the nice thing about these is they are always 1/3 area of the base times the height. So just like a triangle was 1/2 base times height, when you go into three dimensionals, right? Triangle was 1/2, two dimensionals. Three-dimensional kind of triangular shape, right? Because it comes to a point, is 1/3 base times height. Only now it's area of the base times height, and area of the base for a circle is pi r squared. Look at how this one works. 1/3 s squared h, because it's a square, right? So the bottom, the area of the base is s times s, which is your s squared. So again, it comes down to 1/3 area of the base times height. All right, let's look at how we can apply some of these formulas. Assume you want to build a concrete patio in the back of your house. The patio is to be 18 feet long, 16 feet wide, and 6 inches deep. How many cubic yards of concrete are needed to build the patio? Well, the first thing we have to figure out, okay, we're doing a rectangular object, so volume is very easily length times width times height. So we do 18 times 12, but then we go, 6 inches. Well, we have to have it all in the same unit of measure. So we change 6 inches into half of a foot. So 18 times 12 times a half, and we get 108 cubic feet. Now we have to convert cubic yards into cubic feet. Well, we know that 1 yard equals 3 feet. So if we cube both of those, we get 1 cubic yard, because 1 cubed is cubed, equals 3 cubed, which is 27 cubic feet. If we use that ratio, we can do what's called a unit conversion. We can convert cubic feet into cubic yards, and we'll see that we need 4 cubic yards. Now, this brings up a little technique that I like to teach my students that I call the conversion line, and it's something that makes converting units of measure a lot easier. And it helps you just keep everything organized. Basically, the conversion line is just that. It's a big old line. You start with, your starting measure, the thing that you want to convert. So in this case, 108 cubic feet. You put a little vertical line to let you know that we're going to start doing some math. We're going to do some conversions. And basically what's going on is each of these little spaces, right? You could have, if you're converting it, 3 and 4 times, you got to go through a bunch of different scales to get to your final unit of measure. Think of each of these as a fraction, and each fraction has to be equal to 1. So for instance, if you didn't want to do this work, you didn't want to cube everything out, or you didn't understand this just doesn't make sense to you, well, you could just think of 1 yard equals 3 feet. And I can write that 3 times. And the reason why I have to do it 3 times, well, first of all, notice that 1 yard and 3 feet are the same thing. So this fraction is really equivalent to 1. So when you multiply something by 1, you don't change its size, you don't change its value. You just change the way it looks, because now instead of feet, I'm going to be in yards. Well, I've got 3 feet. That's feet cubed. That cancels feet cubed. And I've got yards cubed on top. So my answer is going to be in cubic yards. And all I have to do is 108 divided by 3 times, which is the same thing as divided by 27, which is the same thing that happened here. The conversion line is just really nice, because then when you want to convert things like miles per hour to feet per second, you can use the conversion line. And it's a very good, versatile technique. Anyway, if a concrete mixer truck holds 5 cubic yards of concrete, how many truckloads of concrete will be needed? Well, because we need less than 5, we only need 1 truckload. That's pretty obvious. Now, suppose you want to build a swimming pool in your backyard, and the city in which you live has a restriction on the volume of water that the pool can hold. The restriction is that pools may contain at most 4,800 cubic feet of water. Your plans are to build a pool that's 16 feet wide, 24 feet long, and has a depth that varies from 2 feet to 12 feet on a constant slope, i.e., if you look at it from the side, it's a triangle, which you always want to draw pictures for word problems, right? If your word problem has anything to do with shapes and stuff, draw yourself a picture. So here's the side angle, right, of your pool, where it starts here at a depth of 2, and it finishes here at a depth of 12. And then your length across here is 24 feet. And then, of course, the width, if you went in that direction with it, would be 16, right? If you want to kind of look at the top of it, if you want to try and make a whole three-dimensional thing out of it. Okay, so if we want to figure out the volume of this thing, we need to cut it up, because if we just draw a line straight across here, right, make this 2 feet thick, we can find the area of all that. And then down here, now this is going to be 10 feet, 24 feet, and then the other dimension over there, right, is still 16. And we can find the volume of that wedge, just like a little wedge of cheese. So we kind of have to do it in pieces. Okay, so this is a picture, kind of a better drawn picture if you can see the blue lines showing you, what it looks like. Now let's break it up into pieces and figure out what's going on. So here's the side shot again, right? And then we're going to have to break it up. Well, instead of breaking it up into the rectangular piece and the triangular piece, we could actually just think of it as a trapezoid, find the area of that trapezoid, that becomes our base, and then the height becomes the third dimension, right? Because think about it, it's almost like you're standing the pool on its side. And you have this base that looks something like this. Right? That's your triangular thing set on its side. I know it doesn't look like a triangle. This one maybe should have been a little bit longer. Maybe something like that. So here's your base. And then your pool is just going to sit on its side. Right? And so when that happens, this becomes your base. If we can find the area of that base times the height here, and in this case the height is this dimension here of 16, right? Because they told us 24 by 16. Then we can find the volume, right? Area of base times height. So the area of the base, we can use our trapezoid formula, which we know is basically the average of our two bases, the two that are parallel to each other, times the height, right? So there's the average. Add them together, divide by 2, times the height. And that gives us, this is 168 square feet, the side of the pool. But when we turn it on its side, that becomes the base, and then we just multiply that by 16. But like I said, the other way is you cut it up into pieces. Find the volume of the top piece, and then find the volume of the bottom triangle. Both ways are going to get you the exact same answer. So if we think of it this way, we can find the area of the rectangle, the area of the triangle, and we can still get that 168 square feet. In either case, once we have that, we multiply it by the 16 feet, which is the other dimension, this width dimension, and we get 2688 cubic feet total. Well, it's said at most pools can contain 4,800. We're much, much lower than that. So we're all good. City's not going to say anything, and they're not going to have any problems. We'll be able to get our permits and build our pool and splash around in the summertime. Okay, how about a third example where we look at a sphere? So you're filling balloons with an air pump. If after 2 pumps of air, a balloon has a radius of 2 inches, find the volume of air contained in the balloon. Also, we want to make the balloon bigger, so they put 2 more pumps of air, and the volume of air doubles. So how much volume of air is in the balloon now? And then how big is the balloon's radius after those full pumps of air? So basically, the volume will double, but what happens to the radius? Does the radius double? Well, we'll have to find out. And the last thing is, by what percentage does the radius increase when you go from 2 pumps of air to 4 pumps of air? So back to the whole thing. If it doubles, it went up, right, by 100%. It was a 100% increase if it doubles. But if it doesn't, we can figure out what percentage it actually goes up. Okay, let's start from the beginning. We can figure out the volume of everything. When the radius is 2 inches, we plug it into our 4/3 pi r cubed, cube the 2, get 8, multiply it by 4/3 and then by pi, round to a couple decimals, right? Because pi is that weird number that goes on and on forever. And we get it's roughly 33.49. I mean, you could really even say it's, roughly 33.5 cubic inches. Okay. The volume doubles after 2 more pumps, so it goes to 66.98 or roughly 67. To find the new radius, we have to kind of solve backwards for our formula, right? We set 66.98 inches cubed to this and solve for r. So the first thing we want to do is get rid of the fraction. So we're going to multiply both sides by 3/4, which gives us 50.235. Then we want to divide both sides by pi to get rid of the pi. And if we do this in the calculator, right, we can get an approximate number, 16. Then we take the cube root of both, right, to get, what r is, and we get approximately 2.52. So that means that the radius is approximately 2.52 inches. Remember, it started at 2 and it went up to 2.52. So that was not doubled. So we can find the actual percent increase by doing the change of percentage over the original percentage. So if we're going from 2 to 2.5, then the from is our original. That's the old radius. The new radius, 2.52 minus the 2, so that's going to be the difference. So difference over original. A difference of 0.52 over 2 gives us 0.26, and then we multiply that by 100 to turn it into a percentage, and we get it went up by basically 26%. It was a 26% increase. Okay, third example. We can see that although the volume doubled, it increased by 100%, right? The volume. The radius only increased by 26%. And that's key to understand that, these things aren't linear. We're talking about cubic measurements. So we're no longer having linear relationships between the two things. If one thing doubles, that doesn't mean the other thing doubles as well. Okay. Now an example about a drum. And the sound the drum makes varies according to the diameter and the depth of the drum, i.e. how much volume of air is inside the drum. And that's, of course, assuming everything else remains equal. The materials that are used to make the drum. Like a drum out of an actual animal hide is going to sound totally different than one that's made out of a synthetic material, and so on and so forth. So let's find the volume of air in a snare drum that has a diameter of 14 inches and a depth of 5. And then a tom-tom drum has a radius of 5 inches and a depth of 8 inches. Find the volume of air in the tom-tom. All right, so let's start with the snare drum. We use the formula, volume equals pi r squared times 8. Remember, it's area of the base times height, and the area of the base is a circle, so it's pi r squared. They told us the radius was 14. Sorry, not the radius. They told us the diameter was 14, which is why we have to divide it by 2, because it's half. The radius is half of that. And we get 7 inches, a height of 5. Plug everything in and get roughly, right, a little bit more than 769 cubic inches. Well, now we can do the same exact process for the other drum. In this case, we have a radius of 5, height of 8. Plug it all in, get 628 cubic inches. It's really just that simple, guys. Remember, it's area of the base times the height. In this case, if it's a circular cylinder, the area of the base is a circle, which is pi r cubed. Now the pyramid, remember this one is 1/3 the area of the base times the height. So you could just do 755 squared times 1/3 times 480. and that will be the volume. And it says a scale model is made out of sand. If the model has a ratio of 1 to 100, what is the volume of sand needed to build the model? Well, once we figure out what the volume is, we know that it's just going to be 1/100th of it, right? 1 to 100, so you just divide by 100. Okay, 1/3 area of the base times height, or 1/3 755 times 755 times 480. Do the math in the calculator and get this big old number, right? 91,204,000 square feet. So a little bit more than 91 million square feet. Well, we know that ratios 1 to 100 means that we just need to divide by 100, like I said. But we're doing, everything's being reduced by 100. All three dimensions, the length, the width, and the height, if you want to think about it, right? So it's in 3 dimensions. So the whole thing is being reduced by 100 in all 3 dimensions. So you could go back and take all 3 of these dimensions and reduce by 100, make it 7.55, 7.55, and 4.8, and then rerun the numbers. Or you could just realize that if it's being reduced by 100, if it's basically being divided by 100 3 times, then it's being divided by 100 cubed, and 100 cubed is a 1 with 6 zeros, or a million. So that means we can now just take this and divide by a million and see that we'll only need a little over 91 cubic feet of sand to make the model. Okay, surface area. Just like a 2-dimensional object, you're just going to add some stuff up. Only instead of adding up lengths of, pieces around the perimeter, here you're going to add up areas of the pieces that make up the surfaces. Now, the surface area of a rectangular solid or a rectangular prism is really easy because you're just going to add up all of the bits and pieces. Now, if it's a perfect rectangular thing, you get this nice little uniformity. Because if you think about the picture, right, here's my rectangular object. We know this top surface and this bottom surface are the exact same surface. We know that this side surface and this hidden one over there that you can't see are exactly the same. And then we also know this front surface and the hidden one in the back are the same. So you really just need to add up this top, this front, and this side, and then multiply by 2 to double for the rest of them. And that's why they give you 2 of this, 2 of that, 2 of that, because it's basically each of these is one of those surfaces, add them up, divide and multiply by 2, or multiply each one by 2 and add them up. It's the same thing mathematically speaking. So if we want to find the surface area of the cake that will need icing, then we have to find this, the areas of all the surfaces that are going to get covered in icing. So it depends. Like, is she going to ice just the top? Is she going to ice the top and the sides, right? The whole darn thing wouldn't make sense because you don't normally ice the bottom of a cake. But we'll see. In this case, they have us finding the surface area of the whole thing. So they're basically saying that she's going to ice everything. And anybody who knows anything about baking or cakes, or who's even just eaten a cake once in their life, knows that you never ice the bottom. But in any case, we can, use this silly little formula and think of lengths and widths and da-da-da-da. Or, instead of memorizing a formula, you can just think of, okay, what's the area of this one? It's 12 times 2. That's 24. I've got 2 of those. What's the area of this one? Well, it's 18 times 2. That's 36. I've got 2 of those. And then what's the area of the top? That's 18 times 12. Figure out what that is. I've got 2 of those if I'm doing top and bottom. And then you get 552. I still think it's kind of silly because who's going to ice the bottom of a cake? But there you have it. All right, skill check. See if you can do this one. Surface area of a cube. If you have a side S, then we know the surface area could just be 6s cubed. 6s squared, sorry, because it's a cube. I had to say cubed. If you've ever seen a die, right, or anything that's a perfect cube, you know that all the sides, sorry, that should be vertical, are the exact same size, right? This area is the same as that area, is the same as that area. So that's why it's going to be 6 times something, because there's 6 sides. And because it's a cube, right, every length is the same, right? So this is x and this is x. So the area of this is x squared, so 6x squared. They just call it 6s squared, s is in Sam, because it's side, s for side. Surface area of a sphere, 4 pi r squared. Just kind of have to memorize that one, unless you know anything about calculus, know anything about derivatives, because the volume was 4/3 pi r cubed. When you take the derivative, the 3 comes down and it goes 1 less. So 3 times this becomes 4, and 1 less becomes squared. And there's surface area. Now you might recall from my other video that the same thing goes with area, which is pi r squared, and circumference, which is 2 pi r. Take the derivative of this and you get 2 pi r. So it's really cool that with circular things, whether it's a circle or a sphere, going from the area or volume, right, something that's measuring more than just one thing, right, so an area versus a volume, to the other portion. So area to circumference, you can see how there's a similar thing between volume and surface area, as far as, you know, like the 2 dimensions to just the circumference, and then the 3 dimensions to just the surface. They're both just derivatives of each other. The derivative of area is circumference, the derivative of volume is surface area. I know none of you probably had calculus. You're like, what the hell does all this mean? It doesn't mean anything other than I'm just trying to point out one of the cool things in math. Okay, Tyson's Athletic Gear Incorporated manufactures baseballs, among us, all sorts of other things. If a baseball has a diameter of 9.2 inches, what's the surface area? And if the quota for a day is to make 225 baseballs, what is the minimum amount of covering material needed to meet the quota in square feet? That's, of course, assuming there's no waste, which, of course, there will be when you're, cutting out pieces of fabric to make a circle. In any case, let's look at what we got to do. Since the diameter is twice the radius, we knew that, then the radius is the diameter divided by 2. We get a radius of 4.6. We throw that into the formula. Bingo, bango, bongo. We've got our volume. Surface area. I'm sorry, we got surface area, not volume. So here's our surface area. Now, to find the amount of material needed to cover the baseballs, we can multiply the surface area by 225, because that's how many baseballs are going to produce, and we get this big old number, almost 60,000 square inches. Now, to find the amount of material in square feet, we got to do that conversion line technique again, right? Where we've got 59798.25 inches squared. We need to convert that to feet. So I know I need to bring in feet and get rid of inches, right? Because they need to cancel. And a 1 foot is 12 inches. But that's only one of them. I got to do it twice because it's squared. So 1 foot over 12 inches. And now these 2 inches cancel with inches squared. And my answer is going to be in square feet. So it's just take this number and divide it by 12 and then divide it by 12 again, i.e. divide it by 12 squared, which is 144. And we get roughly 415 and a bit of square feet of material. And then, of course, you'd want to round up quite a bit because of all of the waste materials. Surface area of a right circular cylinder with radius r and height h can be computed by the following formula, 2 pi r squared plus 2 pi r h. But if you just think of the shape, you can see where this comes from. So surface area is going to be area of this surface and the one on the bottom. Well, those are just those are just circles. It's area of a circle. And we know area of a circle is pi r squared. Well, there's 2 of them. So that's how we get 2 pi r squared. That gives us the area of the top and the area of the bottom. Simple. Okay. Now, this piece. Think about like a can of soup or any kind of can you have that has a label on it. If you cut the label and then unwrapped it, wouldn't you have a rectangular piece of paper? You absolutely would. If you don't believe me, go find a can of something in your pantry and cut the label off. Just make sure you keep the label so you know what's in the can. Okay, but what are the dimensions of this piece of paper? Well, we know the height here is the height. That's our h. But what about this distance here? Well, when you wrap it, it goes around the can. So that ends up being the circumference. And we know circumference is 2 pi r, right? So that's why this is 2 pi r times h, 2 pi r times h. So you take the area of the label and the area of the two tops and you put them together, and there's the surface area of your right circular cylinder. Now, of course, you could always just take all these formulas and write them down in your notes and keep them depending on if you're allowed to have notes or whatnot. But I'm trying to show you how you can kind of logically think through these things in case you're ever in a situation where you have to take a test or something and they don't let you have formulas. So to find the surface area, all you got to do is plug in your values for R and H and get your answer. Okay, so let's summarize some of these things. If we have our rectangular solid, there's our volume formula, there's our surface area formula. But remember, it's just area of the base times height. And for each of these, it's just the area of the three sides times 2, right? You add them all together in times 2, or you multiply each one times 2 and add them together. So don't let the LW, the LH, W, all that stuff confuse you. Just realize that just always draw a picture, and then you could find the area of this shape easily. You can find the area of that surface and the area of that surface once you label what everything is. Sphere, a cube is the same darn thing. It's still area of the base times height. It's just they're all the same thing, so it becomes S cubed. And then same thing for the sides. You're still finding the area of these three sides and doubling them, which just becomes 6 of one side because all 6 sides are the same. Here's our volume, here's our surface area, which in fact is the derivative of that. I know you're going, what the hell does that mean? Area of the base times height, which is pi r squared h, is our volume. Surface area, 2 pi r squared, because that's the area of the two circles, and then plus 2 pi r h, because that's circumference times height. Volume of a right circular cone, well, there's our 1/3 area of the base times height, where the area of the base is pi r squared. The surface area we didn't talk about because it is just a nightmare of a formula to try and figure out. This is one of those things where you would have to memorize it, or they would have to give you that formula, because there's just no intuitive way to see that. Same thing with this one. I mean, it's kind of a bunch of triangles, but because they're slanted, everything becomes tricky, and it's a pain in the butt. But volume is still easy as 1/3 area of the base times height, where in this case the area of the base is S squared. And then here's our really funky surface area formula. Okay, with all those in mind, we can now find volumes and surface areas of all sorts of ordinary everyday shapes, like a grain silo. And it can hold 400,000 cubic feet of grain. There is a limit to the height of the silo of 100 feet. Find an example of a silo that meets the necessary requirements for the farmer's needs. Well, first you got to figure out what the shape of this thing is. It's a right circular cylinder, and they want to find an example, not the example. Because as the radius and the height of the silo can vary, there are going to be many different size silos that meet that same criteria. If we take what we know, i.e. the volume that we're looking for, and the volume of right circular cylinders, the height of the silo and the required volume, if we plug those two in, we can find the solution using our simple formula where R is the radius and H is the height, and V represents the volume. But if all we have is volume, then we could set, H to be something and solve for R. Now, they did tell us that we had a maximum H of 100. So we could just go with that and say we want to make our silo the maximum height it can be and then find the radius that it has to be to make it fit. But it just says it had to be a maximum of 100, so it could be anywhere in between. So we could set it as something less than 100. But in any case, here's our volume formula. Pi r squared, area of the base, times height, 100. We're going to ignore this whole domed roof. We could work with this, but we're just gonna basically say to the top of the flat part before the roof starts. That's the height we're looking at. And if we do this with 100 foot as the height, and we do all the math, we can see that we get 4,000 over pi square feet equals our radius squared. Plug in pi, take the square root of both sides, and we get a radius of basically 35.69 feet. And of course, if we wanted to make sure that it was big enough, it could be a little bit bigger, we'd probably just make it 36 feet. And then it would have a little bit more volume that was necessary, but at least it wouldn't be too small. Here's another example. You've decided to paint the exterior of your house. You need to determine the amount of paint required to do the job. You assume your house is a one-story rectangular building with a length of 87 feet, a width of 45 feet. The height of each wall to be painted is 10 feet, and there are 6 windows of various sizes that we can take away. So draw ourselves a picture. Here's a picture. We're obviously not painting the roof. Here's the 87 by 45, 10 feet tall, and then here are the windows and doors that don't need to be painted. We have to assume some things. How many square feet 1 gallon will cover, in this case 400 square feet, and that it'll apply 2 coats. So that also is going to have a bearing on how much you need, obviously, if you're putting it on 2 coats. Okay, now we need to consider the total area as being the total area of the rectangular object minus the windows and doors. We can do a little shortcut by realizing that the 2 sides of the house are the same, so we just need to find the area of that and multiply it by 2. And then the front and back are the same, so we need to find the area of one of those and double it, and then add those 2 things together, and that's where we get the whole thing of 2 times the area of the long side plus 2 times the area of the short side is going to give us the total surface area. Again, guys, draw pictures, draw pictures, draw pictures. So now we can find the area of this really easy, 87 times 10. This one, 45 times 10, right? Here's our 2 things. One, after we multiply them by 2, we add them together, and that gives us the total amount of area for the whole house. But we now have to subtract the area of the windows. They told us they were 2.5 feet by 3 because they told us 30 inches, which we converted to 2.5 feet, and 36 inches, which we converted to feet. And then the other one, 30 inches by 84, right? Converted to 2.5 by 7 for the door. There are 6 windows, so we do 6 times this, 2.5 times 3. So 2.5 times 3 is the area of 1 window. Multiply that by 6. So there's 45 square feet of windows that don't need to be painted. Do the same thing with the 2 doors. 7 feet by 2.5 feet times 2 gives us 35 square feet for the doors. We add those 2 things together and then subtract it, or just subtract them individually, right? But basically we have the no paint area is the windows plus the doors, which is 80 total feet. Sorry, square feet. We take the absolute total of the wall area, not including windows and doors, and then we subtract those windows and doors, and we get now 2,560 square feet of stuff that actually needs to be painted. Whew. The last step is to figure out how much paint that's going to take, right? So if we first have to double it because we only were looking at, the 2 sides, and then we double it for the 2 other congruent sides. We get a grand total of 5,120 square feet that need to be painted. It told us that you can do 400 square foot of surface with 1 gallon. So you divide by 400, you get 12.8 gallons. And since we can't do, we can't buy 1/8 of a gallon, we would have to buy 13 gallons of paint to complete the job. And I mean, this is what painters do in the real world. All right, that's all I got for you.